Hello everyone, welcome to Notes 9.1, Chapter 9. Man, what a cool chapter, what an important chapter. All things right triangular. It's going to help you guys when you take trig and pre-calc, calculus, if you take mathematics in college. Man, such cool stuff coming at you. And it starts out pretty innocently though, as we take a look at the Pythagorean theorem. I know you guys know a lot of the Pythagorean theorem stuff, so the notes shouldn't be crazy hard for you today. As you can see here on our first page, I brought back an old friend, a little GeoGebra. I know you guys miss GeoGebra so much, so I wanted to just show you our essential question: how can you prove the Pythagorean theorem? And there are many ways to prove the Pythagorean theorem. This from GeoGebra is an area snapshot, a visual representation. So let's check it out. As you can see over here, the side lengths of this triangle, you've got a 3, a 4, and a 5, right triangle. And the Pythagorean theorem, of course, tells us that a squared plus b squared equals c squared. And what does that mean? The two legs of any right triangle, when you square them and add them together, will equal the hypotenuse squared. So I know, like I said, you guys learned this back in the day. And this is a pretty cool way to look at it. So if you take 3, the side we have right here, and square it, that gives you an area of 9. If you take the 4, the base of this triangle, and you square it, that gives you an area of 16. And then if you take the hypotenuse and you square it, that gives you an area of 25. And of course, 9 plus 16 is 25. So to kick off this lesson today, I just wanted a visual proof representation of what we're looking at with Pythagoras' theorem from way back in the day. All right, so here it is from our textbook, the actual theorem itself, theorem 9.1. And of course, you just have to keep straight with the hypotenuse is, always along the side, always the side across from the right angle. And the legs will be referred to as the other two sides of the triangle. All right, now Pythagorean triple, very important. When you guys take your SATs, Pythagorean triples are going to be huge time savers for you. And what are they? Well, it's a set of 3 positive integers that satisfy the Pythagorean theorem. And the most basic one, the one you'll see a lot, is 3, 4, 5. Because 3 squared plus 4 squared equals 5 squared, just like we had back in the GeoGebra example. Now the cool thing is, any multiples, if you double all of them, 6, 8, 10 works. If you triple all of them, 9, 12, 15 works. And any value of x that you would multiply by each of those numbers is going to work for you. Or the second most common one, 5, 12, 13. And again, any multiples of those are going to work as well. And you have a couple extra ones here that are popular, 8, 15, 17, and 7, 24, 25. So if you see on an SAT, if you're like, oh, you have a 5 right here, and a 12 right here in a right triangle, don't waste time plugging this into Pythagorean's theorem. Just remember your triples, and it's a gigantic time saver. All right, first example today. I'm going to try to write the least amount possible because this pen's sloppy. So I went with the book answers here. So the book solutions. Find the value of x, then tell whether the sides form a Pythagorean triple. So, setting it up with Pythagorean's theorem. You see what we got? We have 5 squared plus 12 squared. Ooh, and there's one of those triples that if we recognize that we wouldn't have to do any of this. But here's the actual work for it. So you plug it into the theorem. And don't forget to square everything. So 25 plus 144, 169. Square root of 169 is indeed 13. So it forms a Pythagorean triple because you have 3 integers, 3 whole numbers. So if that's the case, 5, 12, 13, then yes, indeed, it is a Pythagorean triple. Moving along. Now in this example, we're missing one of our legs. So we're given the hypotenuse, and we are trying to work it backwards now. And let's see what we got. So 7 squared and x squared is equal to 14 squared. So take the squares of those things and subtract 49 on both sides. And when you take the square root of 147, we're going to talk a little bit about this a little bit more in a second, but you break it up into square root of 49, square root of 3, and the square root of 49 is 7. So 7 roots of 3, and that is not an integer or a whole number. So they do not form a Pythagorean triple. You can still find what it is, it's just not a whole number. And most of the time they're not going to be whole numbers, but that is okay. So now getting back to this, let's take a little side note here, a sidestep from this section. And this again takes you back to Algebra 1, or pre-algebra even. And let's talk about simplifying radicals here real quick. An example, if you're given a number like 128, and you want to see if you want to break that down, you want to be in simplest radical form. The SAT will be in simplest radical form. They won't have answers that are square root of 128 in their options. It'll be broken down just as this one was. So your mission is to find a factor of the number inside the radical 128. So you want to factor it, and you want to look for one of the perfect squares. So you should be able to generate the perfect squares pretty quickly. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, etc. And usually you can just go up to 100, 9 squared, 10 squared. So these numbers should be familiar to you, and you want to see if one of those numbers is a factor of the number that you're given. So 128, we recognize that 64 goes into 128, so you break it up. Split 128 into 64 times 2. And the reason you do that is because the square root of 64 is a perfect square, so you can bring 8 outside of the radical. So then 8 roots of 2 would be your SAT answer, or your simplest form answer. So let's practice a couple of these down here below. You can pause the video if you want. I'm going to go ahead and do them, and you can see what you got. So rolling along here, it's 75. I recognize that 25 times 3. Why did I pick 25? Because the square root of 25 is 5. So 5 roots of 3, final answer. 270, I know that can be rewritten as 9 times 30. And the square root of 9 is 3, so 3 roots of 30. Now, the 30, why don't you break 30 down? I can go 6 and 5, 3 and 10. Well, none of those numbers are perfect squares. None of those numbers are from our list. So if none of the numbers are on your list, then you just stop right there, and that's your answer. You can't always break a number down. Not every number has a perfect square hidden inside of it. And then this last example here, 48. Check this out. There's a couple different ways. Sometimes you don't find the largest one first. If we do, then we could break this into 16 times 3. So that's 4 roots of 3. But say you didn't recognize that 16 was it. Say you went after 4, because 4 goes into 48. So what if I did square root of 4 times 12? Well, that's 2. Square root of 4 is 2. 2 roots of 12. But now 12 can be broken down again into 4 and 3. So that will be 2 times square root of 3, or 4 roots of 3. So it's the same thing, but you want to try to find the largest perfect square that goes into the number inside the radical first to save you some time. All right, so moving along. Example 3, the skyscraper shown connected by a skywalk. Use Pythagorean theorem. So many real-life examples with Pythagorean theorem. So many different ways a right triangle can be presented with a missing side. And so here's just one of them. Each support beam forms the hypotenuse of a right triangle. So you can just set it up. You can see where your triangle is. You got 23.26. You've got 47.57. And you're missing the hypotenuse. So there's just a simple real-life example. All right, so go ahead and pause the video here and try the monitor progress problems that you see coming up ahead. All right, so hopefully you're back to me now. And here we go. The first one, Missing the hypotenuse, so 4 squared plus 6 squared is x squared. 16 and 36, you've got the square root of 52. Now when you break 52 down, 4 is a perfect square that's hidden inside of 52. Rewrite 52 as 4 times 13. Square root of 4 is 2. So 2 roots of 13. It's not a Pythagorean triple. So this one wanted you to answer that question as well. So that is no, because it's not an integer. The second one, oh, look at this. I'm good, man. I see 3 and 5 as the hypotenuse. I know right away my Pythagorean triples, 3, 4, 5. I don't even have to do any work for that one. Then number 3, now this one, when it comes at you with how far from the base of the pole is each wire, then they're looking for, on a quiz or something, you would, or on an SAT, they would say round it to the nearest blah, blah, blah. Actually, when you have an answer like 2 roots of 13, that is actually an exact answer because you didn't round it. You didn't extrapolate it, take the square root of 13 into your calculator. So if the SAT refers to an exact answer, then they're not going to want you to round it out. They're going to want you to leave it in simplest radical form. Most of the time, they'll just say simplest radical form, though. All right, let's keep rolling. Cool thing about Pythagorean theorem, man, this theorem is going to allow us to not only find missing sides of right triangles, we can tell what type of triangle we're dealing with. So the converse, or the flip of the Pythagorean theorem, says, all right, well, what if I give you 3 numbers? You should be able to put them into Pythagorean's theorem and tell whether or not you have a right triangle. So if it satisfies Pythagorean's theorem, then you have a right triangle. So let's take a look at example 4. Tell whether each triangle is a right triangle. So the first one, all right, so I take the hypotenuse, and you don't really know what the hypotenuse is based on how it's drawn, but the square root of 113 is the largest number. So you could put it in your calculator and see that it'll be greater than 7 or 8. So you always want your hypotenuse to be your largest number. So you take the 2 smaller numbers, so in this case 7 and 8, they go on one side of your equation, and the square root of 113 goes on the other side. And then don't forget to square everything. So 113, question mark, 49 plus 64, and they do indeed equal each other. So A is a right triangle. Part B, get this out of the way, is not, however, because the numbers are different whenever you square everything. So again, I put the 2 smaller numbers on one side, I put the larger number on the other side, I square everything. Now here's a good algebraic review of this. When you have a number outside a radical and you're squaring it, you square the number outside, which is the 4 in this case, and then you also square the radical. So when you square the radical, it's nice because it just disappears, just like we did up here with 113 squared, or square root of 113 squared was just 113. All right, so it was a good review. And again, let me make it bigger here for you to accentuate this algebra concept that you may have forgotten. When you have this situation, you're going to square the 4 and square the square root of 95. So that's why it gives you, when you square the 4, you have 16, and you're going to multiply. It's an implied multiplication in between there. So 16 times 95. All right, so that's where they're getting the 1520 on the left-hand side. All right, we got some monitoring progress is coming up, so pause the video here and see what you come up with. All right, when you come back, let's see what we got here. Number 4, tell whether it's a right triangle. So I got 9 squared, 15 squared, question mark, 3 roots of 34 squared. And yes, this indeed works. And again, here's that situation where you take 2, or I'm sorry, you square the 3 and you square the square root of 34, so that's 9 times 34. So there's 306. Number 5 does not work. Again, take the 2 smaller ones and put that on one side. And the larger one is acting like your hypotenuse. This one does not work. So it's a no. All right, and our final concept today, we can take that a step further even, guys. And not only can we tell whether or not you have a right triangle, but you can also determine whether or not your triangle is acute or obtuse. So let's see what we've got. It's like they're playing a game with each other. So it's like A and B are playing against C. A and B are playing against C. If A and B are greater, if they're able to beat C, then it's acute. But if C is like, man, and it's winning, then you think it's got to be a really big side of the triangle. So you got to have an obtuse triangle if C is going to beat A and B added together. Main thing is do not forget to square everything. All right, now this throws it back to something we did earlier this year also. First, you have to verify whether or not the segments can actually form a triangle. So you guys remember how we did that. I give you three numbers. You tell me if they can make a triangle. So that's your first step. And really, this is overkill from what our book's telling us, but we're going to use the triangle inequality theorem to verify that it forms a triangle. But all you have to do is take the two smallest ones and see if they can overtake the larger one. These two here are going to always work if this one works. So you really don't have to do it 3 times. Just take your two smaller ones and see if when you add them together, if they are greater than the third. Because it's kind of like that situation where will the sides meet? You know, you don't want to get stuck with something that's not even make a triangle. So once you determine that it can make a triangle, then you plug them into Pythagorean theorem and see what happens. All right. So again, you take the two smaller ones. So in this case, the 4.3 and 5.2, don't forget to square them because it's using the Pythagorean concept. And it's playing a game against the 6.1. Square everything, you end up with a situation where the A and the B, when squared and added together, are larger than the C squared. So that gives you an acute triangle. So on a quiz, it'll be like, is this right, acute, or obtuse? You put them into Pythagorean's theorem, square them, see what happens. But again, don't forget to make sure it makes a triangle. All right, last couple of monitor progress. Go ahead and pause the video one last time. All right, back again, wrapping things up. 6 and 7. Verify that segments with lengths 3, 4, and 6 form a triangle. So 3, 4, and 6, you know it. So 3 plus 4 is greater than 6. So yes, I can make a triangle with those three numbers. So then you square them and you'll see what happens. 3 squared plus 4 squared is less than 6 squared. So that means you're obtuse. And then the decimal one. First off, does it make a triangle? You know it. So then square everything, see what happens. 3.5 squared compared to 2.1 squared plus 2.8 squared. So look at that. Oh, they equal each other. If you get the same thing on both sides, then it's a right triangle. Oh yeah, of course it is. That's the game we've been playing. So there you go, guys. A squared plus B squared, C squared. You know it. Equal, greater, less than, all kinds of good stuff. All right. Thanks for watching. Peace.